Hi folks, welcome back. I hope you're all doing well. So if you've used ChatGPT or some other LLM to solve coding problems, you're probably familiar with the pattern of then using the LLM itself to also fix problems in the code that it suggested to you. And usually what people will do is try to run that code through a unit test. And if it throws an error, take the error itself and pass it in as a subsequent prompt to the model. And sometimes the model will fix its initial code suggestion for you. That whole flow is called self-repair. This paper we're looking at today tries to make that much more rigorous and tries to come up with some numbers around when self-repair works, how often it works, whether it works better with GPT-3 or GPT-4, and tries to get concrete metrics around all those questions. This diagram shows the basic self-repair code generation loop that the authors are working with in this paper. And you start with the user giving a programming problem to the code model. And along with the problem, you also provide a set of unit tests. And then you see how many of the unit tests are passed by the code suggested by that code model. And if all of them pass, then we're done. If not, some of the failing unit tests can be used as additional feedback prompts. And those are fed into a different model, a feedback model. So in the general case, the code model and feedback model could be different. Usually when most people use it, it's the same model. The job of this feedback model is to provide additional explanation for why the initial code suggestion broke. And then that is fed back once more into the code model. And we hope that using the explanation that the feedback model generated, the code model will now produce correct code. So that is the entire code suggestion plus code repair with feedback loop that the authors are looking at in this paper. Before getting into the experiments and results, let's look at this new metric that the authors are proposing for how to measure success. The traditional metric for these kinds of experiments where you want to measure how well LLM is generating code is a metric called pass at, where K is the number of suggestions or samples that you're getting out of your code model. And this metric measures how likely you are to get a correct program for K suggestions, K samples from the code. The problem with that metric is that it's not really measuring the computational expense of pulling those suggestions. So the authors here instead look at a metric which looks at not just how many samples you pulled, but the total number of tokens that you're getting out of your model. And the metric they propose is the pass rate as a function of the total number of tokens sampled from the model, and they call this metric pass. The problems used in these evaluations are taken from the apps dataset, which is a collection of Python programming challenges. It's very commonly used in evaluations like this. It has a range of difficulty, all the way from interview level questions to very difficult competitive coding questions. The two models they use for the experiments are GPT 3.5 and GPT-4. Now in their first experiment, they're looking at GPT 3.5 and they're using it both as the code model and the feedback model. Now in this graph on the left, in the x-axis we have tokens generated from the model, and on the y-axis we have the pass rate. This black line over here is the baseline, which is the pass rate without any self-repair. And you can see that they have different values for NP, which is the number of initial programs, and N feedback, which is the number of repairs that you are sampling per program. And here we see that GPT 3.5 actually doesn't do so well. So all the feedback-based self-repair, which you can see on this graph with these colored dots, are actually below the baseline. They're all below the black line, which is the baseline pass rate without any self-repair. So we see that at least with GPT 3.5, self-repair based on feedback doesn't improve the success rate at all. In fact, it does slightly. If we look at the same experiment carried out with GPT-4, we do see that for higher numbers of tokens generated, the self-repair case goes above the baseline. So we do see improvements with self-repair, but the gains are pretty small. You see the pass rate only improving from 66% to 71% with a budget of 7,000 tokens when using GPT. Now here's an interesting twist in this paper. The authors ask the question, what if we use humans instead of the feedback model? So if you give humans the initial code suggestion and what broke, and ask human programmers to then generate explanations for why that program is failing, and then use that to feed it back into the code model again, how does that perform? And that's exactly what they did, and they found that human feedback actually outperformed feedback from GPT-4 by a huge margin. So in this table, you see that the overall success rate with GPT-4's explanations was only about a third, whereas with human feedback, it was slightly more than half. So that was a quick look at a paper which tries to take a more rigorous and quantitative look at how self-repair for coding problems works with the GPT series of models. And what they found was that it doesn't work so well with 3.5, it works slightly with GPT-4, but if you incorporate human feedback, you get a bigger improvement in the success rate with self. If you like content like this, please consider subscribing, like the video. I hope you enjoyed that.